Hi, good afternoon. My name is Joseph Nyamogo. I'm a student of the University of Florida College of Engineering, and today I'm going to give a presentation on the paper by Robert Mayer and Mark Stevens, titled Distortion in Variable-Capacitance Diodes. Distortion, variable-capacitance diode. So distortion is analyzed using, in this paper, distortion is analyzed using Volterra series approach. Closed form expressions for intermodulation distortion produced by variable capacitance diodes in series and parallel tuned circuits are derived and verified by experiment up to 200 megahertz. The choice of diode capacitance law exponent for minimum distortion is investigated. Distortion in multiple diode connections is analyzed, and the advantages of the back-to-back connection is shown. Introduction. Variable capacitance diodes are useful in the tuning of communication circuits. The advantages of this method of tuning are compactness, ability to place the tuning control remote from the actual circuit, and electronic control of the tuning function using DC voltage. Disadvantage of this method of tuning is introduction of distortion by voltage-dependent capacitance. The general expressions are derived from the distortions. Verified by circuit measurements at frequencies up to 200 megahertz. Some general misconceptions regarding the optimum value of the diode capacitance exponent are corrected. Relative advantages of various multiple diode connections are explored both theoretically and experimentally. So let's start with single diode circuits in parallel. So an example of single diode circuit is the parallel tuned circuit. Vs is going to be our input. Vq is going to be our bias voltage. Vr is going to be our input. This is the equivalent circuit of this circuit. Parallel tuned circuits, so for small distortions, the upper voltage VL can be expressed as a Volterra series as shown in question 1. C is the incremental diode capacitance. Vq is the bias voltage. Using V equals Vq plus V, equation CV can be C of V, the capacitance can be expressed as shown. The Volterra coefficients for the parallel tuned circuit are given by A sub 1, A sub 2, A sub 3, where A sub 1, A sub 2 is shown here. And the experimental work was performed on intermodulation distortion that's generated by two input sinusoidal signals. That is, IS is given by I sub A cos omega AT plus I sub B cos omega BT. When you substitute this into equation 1, you get the third order intermodulation IM3 and second order intermodulation IM2 shown below. The rest of the equations are shown below, and eventually we arrive at IM3 as shown, with P being the P is the average power in the resistor RP. IM3 can also be written as shown in 22. Now, questions 20 and 22 also you can calculate IM3 equals by variable capacitance diode tuning or parallel tune circuits. The term in parentheses in these equations indicates the possibility of eliminating IM3 for a particular value n. And this occurs for n equals to 3 and not n equals 2, as previous papers have suggested. To check the above, theoretical expression, measurements are made on number of variable capacitance diodes. Two of the diodes are conventional diffuse junction with n equals to 0.4, while the third is hyper-abrupt, n equals to 1.6. Measured values of IM2 and IM3 for the MV1652 diode is shown in figure 4. As you can see, there's agreement between the calculated and measured values in IM2 and IM3. All right. Parallel tuned circuits. The coefficients in 5 are determined at each bias point by curve fitting retained from careful measurement capacitance data. The observed behavior was well predicted by 18 and 19, as seen in figure 5 here. Series tuned circuit. In series tuned circuit, you can see once again VS is our input, CS is a coupling capacitor, CB is bypass capacitor, VQ is the bias voltage, and VO is the output. Circuit in B is equivalent of this circuit. For small distortion, once again, VO is expressed as follows with the coefficient B1 in equation is shown, B2 is this equation, B3 is this equation. We also have this other coefficients, D1 and D2, and D1 and D2 are defined as follows. For omega naught equals to omega A equals to omega B, the IM3 of the series tuned circuit is as shown. Now, figure 7 shows measured distortion for the series resonant circuit of figure 6A with diode IM5461. You can see that once again there's agreement between IM2, calculated and measured values of IM2, and the calculated and measured values of IM3. Series tuned circuit now. For purposes of comparison with multiple diode circuits, distortion measurements are made in the resonance circuit of figure 8. CS is a coupling capacitor, and CB is a bypass capacitor. This circuit is convenient for high frequency measurement, as shown in the equivalent circuit 8B. Figure 9 is the result of measurements on the MV21 or 1 diode, which is how, and you can see again the calculated and measured values of IM2 are in agreement. Calculated and measured values of IM3 are in agreement. Multiple diode circuits. Various schemes have been suggested to reduce distortion by variable capacitance diode tuning, caused by variable capacitance diode tuning. Two of these are the anti-parallel diode connection, as shown in figure 10, and Well, two of these interparallel connection and back-to-back composite common cathode connection. Here's our input, here's our output, VQ and VQ minus are the bias voltages. In here, here's the V1 input and V2 input, two input voltages. VQ is our bypass, sorry, VQ is our bias voltage, CB is our bypass capacitor, and here's our output. The capacitance for each diode is represented by power series as a function of the incremental applied voltage. Give in similar fashion to 5, as shown below, as defined in 32 and 33. The minus sign is because of the reverse diode connection in the anti-parallel diode connection. Now, from figure 10, IM2 is at 0. Figure 12 is the distortion compared with measured distortion compared to calculated distortion using MV2101. And I can see good agreement of IM between the calculated and measured IM2 values. IM2 was not measurable. These measurements were made in figure 8, and the lower Q values for figure 12 represent direct comparison with single diode data of figure 9. Distortion data in two figures are seen to be comparable. Analysis of figure 11 is approached again by deriving the equivalent power series for the capacitance of the multiple diode connection. The incremental voltage is shared between the diodes. Let U be the total incremental voltage, and C1 and C2 are defined as shown. The resultant capacitance of the composite common cathode connection is as defined. For match diode, C is as defined in 43. Measured distortion for the composite common cathode connection in figure 8 is an MV2101 is shown in figure 13. See that there's good agreement between the measured and calculated values of IM3. Now, IM2, errors in the IM2, this is the calculated IM2, and this is the measured IM2. The errors are due to sensitivity caused by stray capacitance associated with the bias resistor B. Direct comparison cannot be made with single diode data figure 9 due to different Q values, but the general trend of reduced distortion is observed. In conclusion, the closed form expression have been derived for distortion caused by various capacitance diode in series and parallel chain circuits. The optimal value for diode capacitance low exponent is shown to be 3 for the minimization of third order distortion, but there are practical difficulties in the realization of this distortion now. One of the difficulties is the presence of small irregularities in the CV plus of hyperbaric diodes, which cause anomalous ripples in the distortion characteristics of these diodes. In multiple diode circuits, the superiority of the composite common cathode connection over the interparallel connection is shown to be due to two factors. One is the sharing of voltage across the two series diodes in the composite common cathode connection, and two is the existence of a second order interaction term which causes the now in the third distortion for n equals to 5. Thank you.